Section 3.2, derivatives of log functions. All right, so we have the derivative of natural log of x is 1 over x, so 1 over the argument. Derivative of natural log, not natural log, log base b of x is equal to 1 over the argument times the natural log of the whole base, okay? Now really these are more general form of the top two, so you could really just get away with memorizing this one and this one instead of the top two. All right, so what does this say? This says if u is some function of x, okay? Then the derivative with respect to x in natural log of u is 1 over the argument times the derivative of the argument with respect to x. It's just using the chain rule basically, because this only works for if we have x here. But this one works if we have x squared minus 5x or something. All right, what does this read? This reads, suppose I'm taking a derivative of log base b of u. I put 1 over the argument times the natural log of the whole base times the derivative of the argument. All right, so let's use that here. Find dy over dx. All right, here's my function. So I'm going to have dy over dx. All right, according to this right here, this is what I have because u is just 5x in this case. So what do? I do 1 over the argument. So 1 over 5x times the derivative of the argument, which is 5x. So that'll give me 1 over 5x times 5, or could I say that's 1 over x since the 5's divide each other out? Sure could. All right, what about this one? Well, a couple of different ways I can handle this. Here's one thing I could do. I could use that property of logarithms that says, let's take that 2 and bring it to the front here. And I could rewrite this as 2 times the natural log of x, like that. Notice I have not taken a derivative yet. I just used that property that we looked at earlier this semester. Something like log base b of a to the r is equal to r times the log base b of a. In other words, take that r, bring it to the front. Property of logarithms. All right, now let me go ahead and take the derivative. dy over dx is equal to 2 times the derivative of natural log. What did we say the derivative of natural log of x was? 1 over x. So what does that give me? Just 2 over x. Let's look at part C. Part C, I like to do a rewrite when I have a square root, so to make it easier for me to take a derivative. So we have y is equal to natural log of x all to the 1/2. Now I cannot use that property of bringing 1/2 here. I can only do that if that 1/2 would be on the argument only. But the 1/2 is not on the argument. This is like that. So really 1's on the argument as the exponent. So let's just go ahead and take the derivative how we usually do. We're going to have to use a chain rule. We have an outside, which is something raised to the 1/2, and the inside is natural log of x. So using the chain rule, we have derivative of the outside at the inside times the derivative of the inside. Looks like that. All right, so this part I could say is 1 over 2 times the natural log of x to the 1/2 like that. In other words, bring this down to the denominator and make that exponent positive. Times the derivative of natural log of x is what? 1 over x. So all of this becomes 1 times 1 is 1, 2 times x is 2x, and this I could rewrite as a square root of natural log of x, like that. Now you could leave it as x to the 1/2, that would be fine. All right, let's look at part D. Cannot fit D on this board at the same time. All right, part D is in dog. Part D is in dog. We have y is equal to the natural log of x over 1 plus x squared. Now, if I just go ahead and start trying to take the derivative of this, I have 1 over this stuff times the derivative of that stuff, and I've got the invert fractions, I'm going to have to use the quotient rule and so forth. But what you want to try to do is anytime you have these logs you try to take a derivative of, try to rewrite them first using properties of logarithms. So I'm going to do a rewrite. This is still y. I'm not taking a derivative yet. What do I do with the natural log of a quotient? I rewrite that as the natural log of the numerator minus the natural log of the denominator. That's just using the properties of logarithms. Now let's take our derivative. dy over dx. Derivative of natural log of x will be 1 over x minus the derivative of this is 1 over the argument times the derivative of the argument. Well, that gives me 1 over x minus 1 over 1 plus x squared times the derivative of this is just 2x, right? Well, I could say that's 1 over x minus 2x over 1 plus x squared. And it's a lot quicker if we first rewrite it this way than if we just take the derivative from the beginning. Let's look at part E. E is an elephant. That was D. Let's look at E. E over here, we're going to have y is equal to the natural log of x. Well, that one looks bad, but it's not too bad. All right, so what do I try to do with a logarithm? I try to rewrite it. I don't see a property I could use here to rewrite, so I'm just going to take a derivative. All right, so look at this first of all. How do you take the derivative of the natural log? 1 over the argument, so 1 over the natural log, times the derivative of the argument, so times d over dx of natural log of x. So that's 1 over natural log of x times the derivative of this is 1 over x. And if I multiply, I get 1 over x times natural log of x. Let's see, that was part E, right? All right, let's look at this now. Let's look at the derivative of, let's look at this rule. The derivative with respect to x of natural log of absolute value of x. That's going to equal to 1 over x if x is not equal to 0. All right, let's see. Our example is going to be what? For part A. Let's do this. Instead of calling that A, let's say find y prime. And in part A, we're going to have y is equal to the natural log of the absolute value of x squared minus 1. So I'm going to find the derivative of this. Now notice, the derivative of natural log of the absolute value of x is just 1 over x. But that's only the case with x. If it's anything other than x right here, I'm going to have to use a chain rule to take the derivative of the inside. Alright, so dy over dx is equal to 1 over the argument without the absolute values times the derivative of the inside of the absolute values, x squared minus 1. Well, that's 1 over x squared minus 1 times 2x, or we can say 2x over x squared minus 1. I'll tell you what, let's write a more general form of this one. So let's say the derivative with respect to x of natural log of the absolute value of u, where u is some function of x, okay? what is that equal to? That's going to equal to 1 over the argument without the absolute value times du over dx. Well, that's actually what we just did there. We said, okay, that's like u there, right? So derivative of this stuff is what? 1 over the argument without the absolute value, like you see there, times the derivative of the argument without the absolute value, which you see there. How about b? b is going to be y is equal to the cosine of the natural log of x. Y is equal to the cosine of the natural log of x. All right, let's think about how we're going to handle this one. For sure we have an inside and we have an outside right here. So let's use the chain rule when I take the derivative. Chain rule says derivative of the outside, which is negative sign, at the inside times the derivative of the inside. So this will be negative sine of the natural log of x times the derivative of that is 1 over x, right? Well, if I multiply that, I get negative sine of the natural log of x all over x. Really, if you get these rules down for this section, it's not too bad. Let's see, let me come up with another one here. Find dy over dx. Find dy over dx of y is equal to the log of sine of x to the fourth. All right, so look at this one. What I like to do whenever I have the 4 on the inside is putting it to the outside. So I'm going to do a rewrite. I'm going to say log of sine of x raised to the fourth, like that. Now remember, if we see a property of logarithms, let's use it before we take the derivative. I see a property. I could take that exponent and bring it here. So y will equal to 4 times the log of the sine of x, like that. Now notice this time, I'm not taking the natural log this time. I'm not taking the derivative of natural log. I'll be taking the derivative of log. So what did we just have up there? We had the derivative of, I think we had log base b of u. Let me make sure I'm using the same letters, because different books use different letters here. Let me make sure I'm sticking consistently. Log base b of u, yes. So what was this rule? That's 1 over the argument, 1 over u, times the natural log of the old base, times the derivative of the argument. It's basically what we said. That's going to be the formula we use here. And why? Because that's understood to be log base 10. So dy over dx will equal to 4 times this derivative. How do I take that derivative? I say 1 over the argument. What's the argument? Sine of x times the natural log of the old base. What's the old base understood to be? 10 times the derivative with respect to x of the argument, sine of x. That's just following that formula. Make sure that makes sense. Following that formula. Make sure you follow. All right, I can rewrite this as 4 over sine of x times the natural log of 10 times derivative of sine is cosine of x, right? Now I could do this. I could say, okay, this is 4 cosine of x over sine of x times natural log of 10, and that would be perfectly okay. Some people, what they see right away is they say, okay, I see this thing as 4 over natural log of 10 times cosine of x over sine of x. Then they say, okay, well, I see that as cotangent. So I'm going to write 4 cotangent of x over natural log of 10. And either one of these will be fine. Either one of those will be fine. All right, this is a short section, so let's look at the last example we have here. Our last example says, find the equation of the tangent line. Find the equation of tan line. Now I'm just going to abbreviate because you have the notes here. Find the equation of the tangent line to the graph of f of x is equal to the natural log of negative x at x naught is equal to negative e cubed. Oh, that looks like a mess, huh? Well, really, it's not too bad at all. All right, so if I'm looking for the equation line, the equation of tangent line, y minus f at x naught is equal to m tan times x minus x naught, right? I already know what x naught is, so I can fill that in. I could say e cubed right there, right? Now I need to fill in for this one and this one. All right, so x naught is negative e cubed. What is, okay, that's x naught. What is f at x naught? Well, let's evaluate f at x naught. F evaluated at x naught is the same thing as f evaluated at negative e cubed, right? Which is just substituting in negative e cubed into f. So natural log of negative e cubed. Well, that's the natural log of e cubed, right? According to our properties of logarithms, if that is base e and that's base e, I could drop everything except the 3. So f of x naught is 3. So right here, I'm going to put in 3. Now I just need m tan and to simplify. Let's find m tan. So let's find the derivative of f. F prime of x is equal to 1 over the argument, 1 over negative x, times the derivative of the argument, times the derivative of negative x. So that's negative 1 over x times negative 1. Or I could say 1 over x. So what are we saying? F prime of x is 1 over x, right? We're really saying f prime of x is equal to 1 over x. F prime of x is 1 over x. So what is f prime at x naught? Wouldn't that be subbing this value in for this x? So 1 over negative e cubed. And I guess I could write that as negative 1 over e cubed like that. So that's m tan, negative 1 over e cubed. Well, let's clean that up. So we have y minus 3 is equal to negative 1 over e cubed times this x. And if I distribute it here, what do I get? Minus 1. And if I solve for y, I get y is equal to negative 1 over e cubed times x plus 2. There we go.